I'll try to keep this introduction short, but just a quick overview. David Yates has been working for 25 years in all kinds of research topics of climate, hydrology, and decision support systems, and his educational background goes back to here in Boulder. I see that he's done his bachelor's degree here at CU at civil engineering and continued to do work there for his master's and PhD in civil and environmental engineering. And then we were lucky to get him as an ASP postdoc back in 1996, and he's been here ever since as a productive scientist. So just a quick overview of some of his key accomplishments. He's worked in climate and hydraulic science and has led the water evaluation and planning system in that capacity, known as WEEP, and that has over 55,000 users in more than 100 countries in supporting integrated water resource assessments under climate and socio-economic scenarios. He's also been a key co-developer of WRF Hydro, which is used worldwide and has led to many publications, and also has worked on the long-range energy alternative planning, LEAP, coupling that with the WEEP system, and has done all kinds of projects, including with the private sector, nonprofits, and municipals, water utilities, and doing planning and adaptation to climate, and also has served as a strong mentor to many people here as your early career scientists, postdocs, PhD candidates, has been a PI in multiple projects, and has about 100 publications. So very impressive record, but I'll cut it off there and let's hand it over to Dave.
Well, it's a pleasure to be here. Wow, thanks for that introduction. I was going to try to avoid giving too many dates because it ages me, but he's done it now. So the cat is out of the bag. You guys are doing the math. How long has he been here? All right. So that's all right. That's fine, because now you'll see some pictures and things, and they're like even yellowed and old. So. And as I was putting the talk together, I even thought, I actually am like part of history. So like maybe this is more like a memorial or something. But so, so just what I'm going to do, go through here, is talk about. I'm going to, I thought this is kind of fun. Get a captive audience for me to talk about my career essentially, but hopefully also motivate some science that we can, advance here at NCAR too, because I have some ideas. So I'm going to talk about sort of this work, sort of the origins of some of this systems modeling that I worked on in Cairo and in Vienna, then talk about my ASP postdoc, mainly because it was quite interesting and I kind of diversified. And then I kind of went back to water and systems with WEEP. And I'll talk about that. And then the importance of this water energy nexus kind of reared its head, and when we kind of did some linking of water and energy systems. And then, in fact, recently with Lawrence Berkeley Lab, did some water energy work, which I'll show. Talk a little bit about WRF Hydro, and then just some about kind of like, future stuff. So I'm gonna, time travel here. I'm, going back to, I did a master's at CU, and I did groundwater work. And my professor, which was also Alyssa McCluskey's professor, Ken Strezpek, I was going to leave the university, and I was working at his center, and he said, hey, I've got an opportunity to go to Egypt, and why don't you go do that? It's under the Bureau of Reclamation. It was international programs at the U.S. Bureau of Reclamation. So I went. There's some pictures of me with hair. I know. And there's the building I worked with, the water resources facility. I was in that building when the earthquake hit in Cairo. So that was a clipping that my mom sent me. What else about that picture? I also worked with the Anglican Church, and we helped Sudanese refugees that were there. So we hung out with this is when all of the lost boys of Sudan came into Egypt. So worked with them, and still have friendships with a lot of these people now, 30-some plus years later. And the Broncos lost that night. So it's John Elway had a bad night. So what did I do in Egypt? It was, again, back in the day, this is long ago, the Bureau of Reclamation Reclamation had an international program. I worked so it was in the Egyptian Ministry of Water, and I had kind of two things I worked on. And we weren't the first national water model. This was the Nile forecast system just started, and it's running today, but I got to work on that a little bit. It wasn't the main focus of my work, but I think it was Bulgarian working on the first Nile forecast system where they use satellite remote sensing products to try to forecast inflows into Lake Nasser. And then most of my work was on the economic side, and this is where I'm going to start talking about systems. So I worked with, it's called the Egyptian Agricultural Sector Model. In fact, the professor at the University of Cairo, the American University in Cairo, Hans Lofgren, who's still at the World Bank, who I still go work with at the World Bank, 40 years later now almost. And so we did systems, and my main area of emphasis was taking, it's called the sector model, means it's focused on the agricultural production in Egypt, and it was a linear programming model, and I added water as a constraint to production. And we got, several publications out of doing this. And I was in Egypt for about a year and a half, and off to IIASA I went, and this is in Vienna, Austria. And I'm going to assume that, maybe people don't know what IIASA is, so I'm going to talk a little bit about it. Quite an institution. In some ways, I look at it as kind of a second distant cousin to NCAR a bit, the International Institute for Applied Systems Analysis. And it started way back in 1972 as an institute where Russian and American scientists came together during the Cold War and worked together mainly on energy problems. Remember that, the rumor was the Russians stole the plans for the space shuttle at IIASA. I don't know if it's true, but they do systems work. And again, I'm going to talk more about systems. Systems are transport systems, energy systems, water systems are often conceived as networks, which need to be solved using mathematical formulations. The father of optimization theory, George Dantzig's actually studied at IIASA, where the linear programming algorithm simplex methods were developed. So these are the kinds of tools that I have used over my career solving system and network problems, but primarily focused on water. And so I worked on a global systems model called the basic link system. And here, again, at IIASA, I introduced water as a constraint to production in this global agricultural model called the basic link system. And so I worked with, several, showing, I've got, I show this table, it's a table of numbers, but it's actually interesting because this is 1992, 1993, you see climate models. So we were thinking about climate change then, right? Maybe some of you, I don't know, you're doing the math of how old you were when we were doing climate model analysis, right? And putting these climate change signals into Egyptian agricultural sector models or world food trade models. So that was, so 98 was one of those first publications where I took output from the basic link system and the Egyptian agricultural sector model and, did economic analysis of climate change impacts. So that was IIASA. And then this one's interesting too, because at IIASA, even though I was working on these systems models, my professor, Ken Strezpek, also was, I don't know how he got this opportunity, but it was this program called the US Country Studies Program. And I was kind of queried this, when do people think the UNFCCC, for which we are no longer participating, by the way, but the UN Framework Convention on Climate Change began. I'm like, when was that? And it was in 1992. And so I was at IIASA around this time when the US Country Studies Program started. And that's when, the UNFCCC was commissioned, and they had to, countries that signed up or, obligated themselves under the UNFCCC then had to start doing their country reporting, right? They had to do mitigation reporting, what are their emissions, and they were also doing adaptation. So it's both this mitigation side and the adaptation side. And so I actually got to work with Ken on the US Country Studies Program and got to do some travel. That's where I kind of even traveled. I remember I left IIASA, I went to Mongolia. I got to go to Mongolia, and it was right, crazy, basically after the, not long after the, the fall of Russia, really, or the fall of the Soviet Union, and got to go, drink mare's milk in the middle of out in the countryside in Mongolia, and then do adaptation work on climate with Mongolian scientists. Super cool experience, and I kind of like that was almost I kind of got addicted to international kind of work then, right? It's like, oh, this is cool stuff. But that was mostly what I did there was hydrology. So this, again, I'm doing a lot of hydrologic and water systems work, bringing them into network models and optimization models, and I call it light hydrology, not Earth systems models, sort of simpler approaches to hydrologic processes. And that's where I will lead the talk towards WEAP and other water systems models. But I will, since this is a timeline here, I'll just talk briefly. I got one slide about my postdoc at NCAR because it mainly, I was reflecting a little bit on all of the people that I work with and the experiences that I had in an ASP postdoc. And maybe I was like the poster child of that statement, as you come as a postdoc, do whatever you want. Because I kind of did a lot, right? I started working with Tom Warner, doing a little bit of WRF and MM5 kind of work. I did a lot of work with Cases 97, Peggy Lamone, and Kyoko. That's where I did some work with Kyoko. And radar work, that was after the Buffalo Creek fire. And so we did some flood work with Buffalo Creek and radar data. So I kind of did all these things to maybe define my greatest interest. And in the end, I guess my greatest interest was thinking about how climate change impacts on hydrologic and water systems, because that's kind of after about 96, I kind of diverted towards doing that. And, I don't have many observations. I didn't become an observationalist or a process-based person, but some of those papers that I worked on with Bob Grossman and Peggy Lamone were, I call them nerdy papers, right? Technical around radiometric temperature stuff. But what happened was I realized water systems are significantly impacted by human influences. Here's some time series of the Colorado River at Glen Canyon. The Glen Canyon Dam goes in and the flows completely change. So humans completely alter hydrologic systems, and we should be able to represent those as best we can. How do humans influence hydrology? There's that one, and there's the Aswan Dam one. By the way, I used AI to do this one. Make me a plot that shows the time series. It was pretty cool. So we should have water models and water systems models that can represent these processes, and that's where I started working with WEAP and started not working with WEAP, started working with water systems models. And so what I'm gonna do is take you on a little journey here of what I mean by water systems models, just so you know why is this important, what are their characteristics and attributes. And again, thinking at the end, I'm gonna say, what can we at NCAR do to perhaps become more relevant where our Earth systems models better integrate into water systems models that are more relevant for water managers. So what are the characteristics of water systems models? And I've just listed a lot of ones that are available. Riverware actually is developed at the University of Colorado. My professor, Ken Strezpek, was sort of the grandfather of the development of riverware. And the attribute that you see of all of those are objects. You see every one of these models has, you see reservoirs and their objects. One that we could talk about is this PyWR, which Aubrey and I have had some experience with, some work with the Bureau. It's the only one that we're aware of that's built in Python, which is then perhaps amenable to doing work on HPCs. But one thing that's true of all of these models is they're all developed within, maybe some have Linux platforms, but Windows or all of them, I say, require a user interface. Do you snobby Earth systems modelers who think you always have to script your models, right? You always have to write these scripts and why? But the user interface is key to these models, actually, which makes us think about then how can we become more relevant in merging Earth systems models with systems models? And you're maybe wondering, well, why? And that's what I'll tell you why you have to. Why is there a user interface in all of these? And here, here again is a schematic of what we tried to conceive with WEEP. A water systems model would then have layer onto it hydrologic processes. And that was, I would say, the slide before of all those models. What is unique to WEEP is the introduction of a hydrologic model where precipitation, temperature, meteorological variables are part of the equation. All of those other models, there's not a physical hydrology component to it. So what I mean by that is, let's take the natural watershed where there's, this is, I call this, let's say wharf hydro, whatever, a hydrologic model where you're modeling hydrologic processes, and then you layer on the system, reservoirs, canals, diversions, the infrastructure of managed water. And that's what WEEP does, is it has a simplified, and it's my contribution, if you will, the idea of, hey, I remember, and I'll back around 2000 talking with, and WEEP is technically a licensed tool by the Stockholm Environment Institute, for which I have collaborated on since the year 2000. So we've collaboratively developed WEEP. In fact, I remember it was in 2054. We affectionately call it the green dot was invented. And the green dot was hydrology, where climate variables could go into the model. So we highly used, and partly highly used because it does allow people to do climate change scenarios right within the system. Mass is conserved and the system is represented. So I'll just quickly go through and talk a little bit about, it's a little bit technical in terms of what we do in WEEP. It's objects, and I'll show the kinds of objects that I'm talking about, but objects are things like the catchment. We have a catchment object, we have a demand object, we have a reservoir object. And those objects contain or hold data, and WEEP is built, the foundation is a relational database. And that really is why, going back to why is there a user interface, is the user interface facilitates the ability to create relationships between the objects. And in water systems models, you have to create relationships between these things because there are rules that govern water. And in the Western US, of course, the biggest rule is prior appropriations, right? So you have an upstream user that has a lower water right. He has to let the water pass him for someone else below to take it. So that's a priority, and you have to have a rule to do that. And in Earth systems models, creating those rules is very difficult, right? Almost impossible. But because WEEP is built on a relational database and has objects, we can create those relationships between the objects. So one of the objects we created was the catchment, and this is how we do it in WEEP. We use GIS processing tools, or actually within the tool, we can do some delineation where we take the watershed, a DEM, create important management points, and then subdivide the basin, and subdivide it by elevation band or important points, and then each of those polygons, the final catchment, it's a polygon, right? And that polygon can be a catchment, and that catchment or that object then can contain time series of data, precipitation, temperature, wind speed. Again, there's a simple hydrologic model with WEEP, a lumped conceptual model that computes, does snowmelt processes, does infiltration, surface runoff, subsurface runoff into a river, routes down to the reservoir. And that linkage of the catchment object to the river is then, again, an object of the link. And then the river's elements are links, are objects or links as well that, of course, have attributes. So let's see, next one. So here are the, again, the WEEP as a water systems model. Its foundation is a relational database. There are the kinds of objects that a user can take advantage of, the user uses, redundant, to build a model. And it's graphical because you go, it's a Windows application, you pull an object off and put it on the palette, the object is placed geographically, we reference things with GIS, so shape files, it knows where it is, and then we start making links between these objects, and the database gets built. And that is a powerful thing to be able to do, because then you can build your model, builds and builds and builds, and boy, have I made some complex models in WEEP, right? So, and at the end of the day, all WEAP does is set up a giant linear programming matrix to solve a giant LP, linear program, at every time step. So that's what, under the hood, all these relationships are going on, but at the end of the day, the model solves a giant linear programming problem, which that's what I did for my PhD. So that's how kind of I knew about how to do some of that stuff. So I'm going to go through a quick sequence here of what water planners think about when they talk about, or what WEAP thinks about when it's doing this allocation. Allocation of water under conditions of scarcity and alternative sources, right? In the Western U.S., especially this year, boy, we're going to be really scarce this year is likely, right? Water managers, Colorado Springs Utilities, Denver Water, I'm sure are already thinking about how they're, where are they going to get their water supplies now? So they're under a condition of scarcity. So we have this concept of priorities and preferences in WEAP. So a demand, if you have two demands, those demands could have different priorities, right? Again, prior appropriations, one has a senior right, one is a junior right. You have to have some way to make that allocation. And in WEAP, we call that the demand priorities. And then a user of water can have different sources. He can have a surface water source, a groundwater source, so those are the supplies. And there needs to be some logic of when do they prefer that supply? Do they prefer groundwater? When do they prefer groundwater? California and Arizona, this is happening all the time, where our first priority is taking it from surface water, but if it's not available, we'll take it from the groundwater. And then there are, of course, all sorts of rules that govern how much can we take. So again, with WEAP, you can go build in that logic to constrain those systems. So here, I'll just give you a quick example. Here's one at a given time step. Let's say a river has 100 units of water available and I have two demands. One user wants 70, another user wants 40. They both have a priority 1. So they have equal priority. How do you allocate equal priority given that this is an over-allocated system, right? So it's 110 units of water are wanted, but I've only got 100. So what WEAP does is equally short each, and that's part of the way the LP algorithm is configured. We short equally, we're equitable in our allocation under shortage. And then different demand priorities. So then you can say, well, this is kind of prior appropriation where user 1 is the 40 unit one is a priority 1, the 70 is a priority 2, so P1 has higher priority. And in this case with WEAP, we give full allocation to priority 1 and short priority 2 by 10. And that's consistent with prior appropriations. That's the way, again, the algorithm in WEAP does this allocation, which was my paper in 2025, which, wow, can't believe it's that long ago. But that's what we describe. And here, just different supply preferences, giving just that example where you have two demands, again, a shorted system. This user, I've got a groundwater supply that I can take water from. So in this case, everyone's satisfied because user 2, the 70 unit user has a secondary source. Okay, so I just put this one up because this is a recent, I've just worked on this when I was working in, where was I, Tom? India, thank you. India with Nesha, this guy Nesha. So we just finished a paper, it was really kind of fun, where we compared water systems models. And I was happy we created a theoretical problem to see if different water systems models could solve kind of a theoretical problem. So this is a recent publication. And WEAP, because of the way its demand, priority, and preference system works, was able to solve this problem pretty efficiently. So now what I'm going to do is transition to talking about so how does this go? I'm trying to think of when we started working with the Water Research Foundation in 2005. How did they come to us? I think they came to NCAR because we were thinking about, we're the climate change science people. And the Water Research Foundations, actually, their headquarters are in Denver. And so I worked a lot with the Water Research Foundation, Kathy Miller and I wrote this climate primer in 2005, and I'll say this kind of took off. By doing the primer, we got lots of opportunities to work with a lot of different municipal water providers where we use WEEP. And in fact, the Water Research Foundation adopted WEEP as sort of their official tool. If a subscriber wanted to use WEEP, they could get it. And then I'm kind of listing all, I mean, in the early time, these are others, but as part of working with Water Research Foundation, we worked with lots of different water utilities, and here's a list of them. And I'm going to show, let's see if my next one, yeah, so I'll say, I'll back up a second here. One thing that happened when we started working with the water research utility is, how do you think about bringing climate into planning problems that the water utilities or water agencies are thinking about? So let me I'll say that again, right? So we're building models and we're doing climate change work with WEEP, and WEEP is developing, but people are then asking or having experiences like Colorado Springs, for example, began an integrated water resource plan. And so one of the things that I did is work with like the RAN Corporation, the SCI, to think what are the methods that we should be using to properly go and work with these utilities and thinking about decisions that they make. And so I just, this is kind of an aside, but I'll just sort of the general category of decision support. How do you do that? You can't you have to have some framework to talk about a planning problem. Colorado Springs, for example, was thinking about raising a reservoir, Montgomery Reservoir, outside of the Blue River. So how do they go and analyze the performance of that system in a fair way? Palm Beach, Palm Beach County was thinking of the C51 reservoir, build a reservoir. Can we use WEEP to analyze the performance of this reservoir under current and future conditions? So we developed, and I've got, we have a few publications, I call it a kind of this structured process around decision support, and in the end, we at SCI, we kind of called ourselves the robust decision support. RAN called themselves robust decision makers. We said, well, we're really not making any decisions when we're working with these organizations. We're just supporting them in their decisions. So we did develop this process that we called robust decision support, where we would go in and formally kind of walk through how to think through structuring their problem. And I think that's that paper here. So, analysis-supported stakeholder participatory process, where we formalized it. And I just, show this diagram. And of course, WEEP was kind of at the center to do this. Alyssa knows about XLRM, right? I think, yes, there's some people that have heard this term XLRM, where it's a brand concept around decision support. So I've used WEEP in all sorts of different kinds of applications, but tried to always go back to kind of this structured process. And, I put one slide up, I'm kind of again telling a story of working with all of these water agencies, all of these municipal water agencies, state water agencies. I don't know how many times I gave talks about, I would say, I am the translator of climate change science, done at NCAR, to practitioners on the ground. So that was I kind of felt like I was taking on that role. And I've got a whole set of slides, but I'm gonna show one where I would communicate to stakeholders who would go, well, we want the information out of climate models about the changes in precipitation. And I would say, good luck, right? Because of scale mismatch and precipitation's not a very good prognostic variable coming out of climate models. So we would always have these conversations about the reliability of, data out of climate models. And I've been doing that for 20 years. Casper's doing it. A lot of us in this room have been doing this translation for a long time of how do you communicate the deficiencies for out of climate models. I would always say, if you don't get precipitation at the right place, at the right time, at the right amount, in a hydrologic model, you're not going to get a good hydrograph. You're not going to represent the system very well. So that was, and to Tom Hobson, you see my reference of my K&N paper. He asked me to do that. Because back in the day, I said, well, we some downscaling methods. So I worked on some simpler downscaling methods to try to make time series that I could put into WEAP. WEAP needed data, but I needed data that wasn't, that got precipitation in the right place, time, and amount, and I could run through WEAP. So we did that, and many have advanced beyond my K&N method long ago, but I now use their tools. So anyway, so now I'm gonna give a couple examples of the use of WEAP and in other models, but because California is such a marker for the development of the tool and the work that I did, I have a special busy slide. This is intentional. Our first real project with WEAP, where we had this hydrologic coupling, was an EPA project. September 11th, 2001 was where I was in Davis, California, where we started an EPA project where we worked with this coupled system, where we had a physical hydrology model linked with WEAP, a systems model. And now 25 years later, WEAP is heavily adopted by the state of California as a tool for water resource planning. And it's used in the state water plan. I worked for years on the California water plan update. And then lots of publications where WEAP is used in all sorts of different kinds of applications for municipalities, for environmental flows, fishery work, et cetera, et cetera. So just a list of lots of publications that came out of that coupling of hydrology into the WEAP systems model. So really, in fact, in 2009, that coupling, I think people, oh, that's clever. And we were awarded the ASC Paper of the Year for, I think, really because, oh, that's an interesting idea, coupling hydrologic processes with a systems model. So I'm just going to now go through a couple examples of things that I did with WEAP that I've liked over the years. This was really a fun project with it's the El Dorado Irrigation District. Even though irrigation is its legacy, it's now as much a municipal water provider. They had a drought plan, and they were asking the question, how does our drought plan perform? And it's, even think philosophically, a water provider, when do they declare a drought and tell people to start curtailing and start asking consumers to cut back? I'm sure this year, I'm waiting for it in Denver to see Denver Water's billboards and things of use only what you need. I haven't seen it yet. But when water starts coming short in Denver, all of a sudden their conservation program comes out and starts communicating, use only what you need, because we don't have a lot this year. Why do they stop doing that in other years? They stopped doing it because they need to sell water. They're a huge capital-intensive organization, right? It costs a lot of money to deliver water to you. So organizations like EID, they don't want to declare drought because they need to sell water to cover their costs. So they need so this project was, we evaluated the performance of this drought plan using WEAP. We built, and it's a very busy model because WEAP, again, because it's object oriented and you can make relationships between the objects, we could put the drought plan into the model and evaluate its performance. So there's the El Dorado Irrigation District as represented in WEAP. And then, I internalize the drought plan into the model where you can then see how does it perform. And we actually work with some economists where we actually pulled all of their billing records and built an econometrics model to see who pays for the drought if you don't declare it properly. And that was that paper in 2013. Another example, bring it a little bit more home. I've worked a long time with Colorado Springs Utilities and Denver Water. In fact, there was a project out of the Water Research Foundation, the Front Range Climate Vulnerability Study, where all of the Front Range water providers were part. And so we built a WEAP model for those that, this will, I did this one so you all appreciate where you get your water and how complicated it is. For those from Spain that might not know about water systems. Do you know, Anna, where you get your water? Do you know where you get your water? Okay, so here, this is for you. Okay, big tunnels diverting water, right? There's the Moffat Tunnel, the Hoosier Tunnel. So, Dillon Reservoir is the Roberts Tunnel, takes water out of the Dillon Reservoir, diverts it into the South Platte down here. So, and all of these diversions are under a water right, and you see the date there, 1935, 1937, 1946. Those are the dates of the right. An earlier date is a higher right and a higher priority. You see the lowest number is the highest priority, 1902, Shoshone. Do you guys know what that one is? Does anybody know what the Shoshone is? Yes. It is a power plant. It's a run-of-river power plant that has the senior water right on the Colorado River. So it commands the entire flow of the Colorado River, and all it does is divert water out, runs it through the turbine and back into the river. But when this is called out, all the Front Range providers have to change how they behave. So what did I do? Of course, I built a wheat model. No, so I did. So one of the things that the Front Range providers did was go and talk to Xcel Energy and say, hey, you're 0.25% of your energy production, and you're screwing us all by having the 1902 right. So can we do something to help us? And so there was something called the Shoshone Relaxation Agreement. And so it was an agreement between the Xcel Energy and the Front Range water providers to say, could we reduce the call and free up some water? So we built a wheat model of this system, and it is crazy, especially for Colorado Springs, how complicated their water rights are in the upper part of the system. And so I worked a lot with Colorado Springs to try to get their rights right, so it was representative of what it could become credible. Again, going back to the decision support, if you're going to work with water agencies and they want to see that you're representing your system properly. It was even a bit crazy because Colorado Springs Utilities, they'd be like, we're down in hundreds of acre feet, and I have to tell them, I can't be that precise, but that's what they wanted. So, and here's it's not quite simple. This is the legalese of the Green Mountain Administrative Protocol that I had to go, a lot of this language I translate into WEEP, right? WEEP language of, there's all this language about paper fill, Green Mountain Reservoir. So Dillon Reservoir, everybody knows where Dillon is. If you go north, so downstream, the next reservoir is Green Mountain Reservoir, and that thing it's super complicated because it's meant to as an augmentation reservoir. So it augments flows to junior water rights holders. And so they actually track is there a paper, there's this concept of a paper fill and all this stuff that all of the utilities have to worry about. And even on a weekly basis during the right now they're not, but by starting April 1st, when their demands start going up, they have weekly calls to see how these systems are behaving and if they're in good standing, if you will, against these agreements. So we tried to work on that, and I'll say one thing that too is all of these Front Range water providers, even you'd say conservative Colorado Springs, is thinking about climate change. So in all of the context of these, we also imposed climate change scenarios into the model to look at the performance of the system. So, okay, so now I'm gonna pivot again to, topic number 5 or so, which is water energy nexus analysis. I remember it was a NOAA, SARP. You guys remember the SARP program? Which probably doesn't exist anymore, does it? I don't know. Societal Applications Research Program, as I got a couple of those projects. I remember David Perkey, clever, he was my co-PI at SEI. His opening statement of the proposal was, water is heavy. And that bore, and our reviewers love that. Water is heavy. Oh, that's clever. And so it kind of born the water energy nexus analysis in WEEP with this NOAA SARP project. And WEEP has a cousin that's built within the same modeling framework called LEAP, which is an energy model, and we worked on blending these two things together. And you know, the water energy nexus, it's interesting. I'll show a few examples, but it's kind of hard to, it's definitely hard to model. It hasn't been quite as successful as we thought in terms of the integration of these two models, which is another, probably for another conversation, but we did it. And we have a couple applications where we used it in the Western US. The top plot there is LEAP, where we are looking at energy systems. The bottom is WEEP, and I did build, I built a WEEP model of the whole Western US, the Colorado River system, and California all tied together because we wanted to get the hydropower signal that goes back to the energy model. And then of course, water is energy intensive, right? Lifting it, pumping it. In California, what do they say, 20, maybe not 20%, but a huge portion of electricity is used in California just to move and pump and clean water. So the water energy nexus, and we did some of that work. And just, this is the kind of thing comes out of the model is the portfolio of generation under different alternatives. And I'll show one more water energy nexus analysis project that I worked on. And I've worked on it recently. This is under the hyperfacets project people might be familiar with, where we linked it to an energy model. This is mostly just, well, this was LEAP, I think. Yeah, this was the energy model. Anyway, but California, of course, when it's, California has these very aggressive emissions targets. And the question is, can they meet them with, solar and renewable energy, especially if hydropower generation goes down? How can they make up for that? You got to get the whole, WEC is the Western Energy Coordinating Council, so the domain, that red area, is all of the Western US's coordinated energy system. California gets electricity from Hoover and Meade, so you have to put those things into your model. This is the last one of WEEP and LEAP. This slide is a new, this is called a different project, where there's no LEAP here, there's no energy model from, the LEAP model's not here, but the energy model's a different one called Switch. And this is where I worked with Lawrence Berkeley Lab, Julia Sinai, and she was the Switch modeler, I was the WEEP modeler, and we kind of soft coupled these models together. And Switch is a portfolio optimization energy model, again, looking at the question as you move forward in under climate change scenarios, and you have changing hydropower, changing wind and solar, what happens to your portfolio mix. And so this model on the water side is quite detailed. I'm going to go and driven, I should say, driven by the red areas there are switch load zones. So, if you go into California, if you go into LA, which is my next slide, it's very busy because it's its own load zone because there's so much population there. The bigger areas are less population and less energy. So we actually, built models of each of the little load zones, and that we could, model the energy use and the energy use by the water sector, and then we're not modeling energy use, the water sector. It's always hard to go back the other way of the energy use, water sector for the energy use. It's hard. We're not modeling the water use by the energy sector here, right? Yeah. The nexus is hard. It's hard. Our brain doesn't work very well circularly. I never did. So, and here's what comes out from the switch side. Again, looking at the portfolio generation under alternative scenarios. And again, not just giving a high level, hopefully you get the big idea. This is an energy model where we're running it into future scenarios under alternative objectives. Is California going to reduce or increase its renewable energy portfolio? Those kinds of questions are meant to be asked. Okay. Now, the other thing that I've worked on over the last, I think the first time We implemented wharf hydro. I surprised Mary by saying that if it wasn't for John McHenry, who we're working with now here at NCAR on a project in Indonesia, but if it wasn't for John McHenry, that we had a project in Romania where wharf hydro first started in, I would say, 2008. Dave Gotchis and I and John McHenry did a project in Romania where say wharf hydro was born. and then it went on to become the national water model. But that's, so for those that don't know when did wharf hydro what was its first instantiation, it wasn't the national water model. It was a project in Romania, which I've learned that model is still running, by the way. Yeah, so John tells me it's still going now, almost 20 years later. So what was my contribution is the reservoirs and the channel network and the routing methods. And Ryan, I'm sorry, the Fortran code's no good, but that's your job to improve it. My job was just to conceive it. Your code sucks, Ryan says. I know it does. Sorry, Ryan. So, but we did it, right? I mean, the national water model, is some way we could say, it's not perfect for sure. It was a concept and an idea, and we did it. I heard Aubrey today, we were talking about Hawaii. I guess there's flooding in Hawaii. Aubrey, you shouldn't, I'm sorry. You know what you said today. You remember? Do you remember? Nobody looks at it. Is it still running? Yes, I don't think anybody looks at it. Anyway, so. So certainly the challenges of implementing reservoirs at this scale, right? Again, unlike WEEP, there's no relationships here. We don't have any rules that describe the governance of these reservoirs. There's models that are modeling the behavior of the reservoirs, the releases, but there's no controls, there's no rules to define them. So we use in my contribution, worked with Laura Reed to finally write a paper about it, to describe the routing and the reservoirs. It's a level pool scheme, and it works. It actually works pretty well when it's given the right parameters. But the challenge in an Earth systems model, where you have a net CDF file where the parameters are roughly static, is changing those parameters. Think of a reservoir. Somebody's operating a valve, turning a valve, changing, opening something, and representing that in an Earth systems model. I would contend, at least today's way we do it, is impossible. So here, there's the upper figure there, the reservoirs. There's an orifice, there's a spill, and there's coefficients that describe those things. And I've actually worked on a project here in California recently where in fact, Ryan and I worked on putting a temporal element to the coefficients of the reservoir, and I was able to actually get a good behavior of the reservoir. But it was difficult, right? It wasn't, I had to go in a net CDF file and change attributes. Whereas in something like WEEP, I could just write rules. So a challenge. So, that one I'm gonna skip. Okay, so my last slide, if, Barlage, if you're listening, this one's for you, because he said, because he's making fun of me because I put AI into my talk, and he knows I know nothing about AI. So he goes, so I made that obviously is an AI-generated slide. So my query was, make an Earth systems model that's linked to a water systems model, because and make it pretty, and that's what it did. And I even did a couple iterations. I'm like, this looks like something out of a, like it's ridiculous. It's ridiculous. And I even said, make it less ridiculous, and it still kept it ridiculous. But I think, there's this opportunity. I think there is an opportunity in Earth systems models where how can we take an Earth systems model kind of approach and from the top down and bring in a systems model where we can have rules and governances of objects, of reservoirs, that makes it more easier to create these kinds of models. I was even on a call with Pat Reed, who some of you might know that name, and he's a really good systems modeler. And we were talking about AI, because this project, it's the hyperfacets project, which is, you have to use AI, somebody said in the background, and they said, but he said, yes, but for systems models, like they're like WEAP and MODSIM and Riverware, they're just, where there's human rules, and I call it unstructured data, unstructured relationships. AI is going to be challenging. How do you, you saw my 28 pages of legal description of the Green Mountain rules and that water managers are worrying about. Is that amenable to AI? I don't know. And do we, as climate scientists and hydrologists, do we need to go to that level of detail? But it would, I could say I have my kind of a dream, by the end of my career, that there would be, I could take like Wharf Hydro and really do something meaningfully with it from the system perspective. That would be really, that a water manager would go, oh, that's cool. WEAP, again, is a Windows, it only runs on Windows, right? Because it's built, all right, and that's one of its drawbacks, but it's also one of its strengths. But can we, and there's some Python tools coming out, some systems Python tools that maybe we could integrate into an Earth systems model. So hopefully we can do that. So that's it. Thanks.
Thank you for that excellent talk. It was really interesting and a great example of how RAL really makes a difference in people's lives, in all our lives here. So happy to take questions in the room and also online. For those online, please do use Slido. But first of all, we have Sue.
Great talk, Dave. A two-part question. First, could you get a little more specific about how you put climate change info into WEAP? What variables, what model do you get it from? And then the second part is, could you give us examples of how some utilities may have used that information to make decisions differently?
Yeah. So practically, one of the things I worked on with SEI was being able to read NetCDF files. So we can read NetCDF. We have a database. We have an EVA database of the CMIP5 archive that we pulled down online, and we have some tools within the model that do the translation. We bring, daily precipitation, temperature, humidity, and wind speed. Those are our 4 meteorological variables, typically at a daily time step. WEAP, kind of the minimum time step is a day and longer, but, practically, even mining the NASA, what is, Casper, what's the data set? What's the NASA one? Bridget's? What's that one called? I don't know.
It's the 25 kilometer grid data set. Statistically bias corrected and downscaled to 25.
Yeah, so WEAP is able to go read those time series, and within it we use GDAL to write, and GDAL, which is a GIS processing engine, to go and do the translation to the catchment boundary and those elevation bands as an example. So I get for a catchment, let's say the upper blue 3,500 meter elevation band, I get a unique time series of precipitation, temperature, humidity, and wind speed. And then at the next elevation band, I'll have a different time series that goes right into the model. WEAP, the ultimate translation, though, is an ASCII file, right? So the NetCDF file is converted into ASCII, for which we stick into the relational database. And your second question was an example of a decision, right?
How does it change decisions for water management?
Well, in fact, it was one of the quotes I forgot to mention in my, my experience of working with water agencies and planners, it's often I go and work on a planning problem. Colorado Springs Utilities want to raise a reservoir, or Palm Beach, they want to build a reservoir or whatever, or essentially do an integrated water plan. And I'd write a report that I would say would go and sit on a shelf. I mean, do we all kind of go, oh, I'm writing a report, no one's going to read it and sit on a shelf? And then I turn and say, it's the process that's which is as important as the outcome. You know, my quote is Eisenhower, the Eisenhower quote. Planning is everything, the plan means nothing. It's the process that matters more than the outcome. And you know, I remember like for Palm Beach County, you got in like Trout Unlimited, maybe not Palm Beach, it was a fishery group. This group came and this group came, disparate interests came together and we built a model. And the model was just almost a place where discussions could happen. And did they really care that much about the outcome? I don't know. In fact, in Palm Beach, it was a process where somebody already wanted to go build the reservoir. So it was already kind of a thwarted process. But I have to always remind myself when I go work with the planners, it's the process that matters more than the outcome, because most likely my report's going to sit on a shelf. Colorado Springs, I don't know what's happened with raising Montgomery Reservoir. I have to ask them. But they're. In fact, I just yesterday talked to a guy that I've worked with for 10 years, and he's asking about the data that I put together 5 or 6 years ago, because they're revisiting their integrated water plan. Right? They're mandated to do it every 5 or 6 years. And I would think that it's as much for the process than the outcome. So.
Okay, we have a question online from Elizabeth Mays. This is about agriculture. Sounds like the primary focus when developing these models was to predict water as a constraint in terms of agriculture. How do they perform when addressing water as an overabundance in terms like flooding and the impact on agriculture?
Great question. We do have applications. In fact, some work in Colombia and by Hector Angarita. He worked with WEEP on the catchment object to include flooding, but I wouldn't say it's not flash flooding, but big system flooding, big river floods. And so we have some papers on using WEEP for large river basin flooding, because it doesn't, WEEP as a systems model doesn't, you know, there's no, we're not propagating flood waves down a river, but we can, let's say at a daily time step, represent flood inundation moving out of the bank into the bank, and Hector did that work with WEEP now a long time ago. Agriculture, I mean, you know, WEEP really is a modeling framework. There's lots of applications of it for agriculture. We put in specific agricultural models. So the green dot that I said is a catchment. It has land use, and that land use can be an agricultural land use, and that agricultural land use can have agricultural attributes, like, you know, soil moisture deficit leads to a reduction in yield, and you can do a model that way. In fact, I had a project in Lesotho where we looked at agriculture and its impact on, or if you're shorted water, how would yield change? Because WEEP really is just a modeling framework. In fact, one of the analogs that you guys are, some of you are probably too young. Do you remember that Microsoft used to have a tool, Money? Or like money, you know, why would you go use, instead of a spreadsheet, why do you use like, what are some of the other financial tools? This thing's listening to me. So WEEP, I said it's kind of, you've used this analogy. Everything that I do model in WEEP, I could probably do in a spreadsheet. Because the power of a spreadsheet is, you know, you can make a time series, you can create relationships. I mean, but, you know, when I go out and work with water utilities, by far the spreadsheet is the primary tool that these people are using, right? They're not using HPCs, right? They're using spreadsheets. So they're very familiar with spreadsheets. But WEEP, in some ways, is a water-centric spreadsheet, right? It has all of the constructs of water, and then all of those object types that allow you to create those relationships between those objects. So you can make a model of kind of anything. Agriculture, people have done agriculture. It's got, you know, we have thousands of publications using WEEP for various applications.
And let's thank our speaker again.